Chapter 2.5, Implicit Differentiation, Day 1, Integrating Implicitly with Respect to x. Review, find dy dx. We've done problems like this before, and every time we've done them, we've solved for y. So let's solve for y first. We'll subtract 3x squared and divide by 6. And then we can find dy dx. And we get negative 1x is our derivative. Today, we're going to look at another way of doing this problem where we do not have to solve for y first. This is called implicit differentiation. Basically, what's going to happen is we're going to have our function. It's not going to be in terms of y, it's just going to be written out. And every time we take the derivative, we're going to apply the chain rule. And if our variable is not x, it's going to be implied inside of the y. Because most of the times we solve for y, like we did here. But now we're not going to. It's going to be implied that there's a y inside of the x. And we're going to use like the chain rule on it. Steps for doing implicit differentiation. First step, differentiate both sides of the equation with respect to x. Don't need to solve for y, just differentiate. Anytime you see a y, you're going to imply the x inside there and apply the chain rule. Next, collect all terms involving dy dx on the left side, move everything else to the right. They're going to factor dy dx out of the left side and then divide both sides so that dy dx is alone. This will become more clear as we do some problems. All right, so let's redo number 2. I had a previous problem stuck up that I deleted. Let's redo this problem implicitly. So first, what we're going to do, excuse me, is derive both sides as if it's an ordinary function. Take the derivative with respect to x of 3x squared. Well, that's 6x. All right, and then we're going to take the derivative of 6y with respect to x. Since it's y, not x, it's going to be implied that there's a function inside there that contains x. And we're going to apply the chain rule. So it's going to be 6 times the derivative of y, which is 1, and then the derivative of the function inside of y, which we don't know, so we just call it dy dx, equals, and then the derivative of 24, that's a constant, so that's 0. Now we want to get all the dy dx on the left side and everything else on the right. So we will subtract 6x. We're left with 6 dy dx equals negative 6x. And divide out the 6. Dy dx equals negative x, which, if we look back, matches our derivative when we explicitly solved for y first. In this instant, that probably didn't make it much of a shortcut. However, the next couple problems, you'll see why it's easier to leave it implicitly implied that there's an x inside the y. So let's look at this problem. Find dy dx given that y cubed plus y squared minus 5y minus x squared equals negative 4. If you were to try to solve this for y, you would have a really hard time because it's a cubic. And cubics are tough to solve. So that is why we do this problem implicitly. So we will start, we'll take the derivative of y cubed with respect to x. First, what's the derivative of y cubed? The outside function, something cubed, would be 3 times something squared, and there's a function implied inside of the y, and the derivative of that is dy dx. And the same thing with y squared. The derivative of something squared is 2 times something to the first power, And then the derivative inside of the y, it's implied. There's a function in there. Derivative of that is dy dx. Minus derivative of 5 times the variable is 5. And then using the chain rule, there's a y there. Derivative of that is dy dx. Minus, now x is the variable we're with respect to, so we can just go 2x equals the derivative of negative 4 is 0. Now the next step, we want all the dy's on one side, everything else on the other. The only thing I have to move over right now is negative 2x. So we got is 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. Next, we want to factor those dy dx. Every term on the left has dy dx, so we're going to factor that out. When we do that, we're left with 3y squared plus 2y minus 5 equals 2x. And finally, we can get dy dx by itself on the left side if we divide both sides by 3y squared plus 2y minus 5. So our final answer, our derivative of y with respect to x, is 2x divided by 3y squared plus 2y minus 5. Now keep in mind, dy dx doesn't mean that y's are on top, x's are on bottom. It's just the rate of change of y with respect to x. And x may be on top in the derivative, may be on the bottom. Same thing with y. But the relationship of our tangent line, it follows the formula given there. Let's do another problem. X squared y plus y squared x equals negative 2. Find the derivative. All right, we'll start right here. We need to apply the product rule because that's a multiplication. So we'll go first function, which is x squared times the derivative of the second. The derivative of y is dy dx because it's 1 times the inside function. So first function times the derivative of the second plus the second function times the derivative of the first. Derivative of x squared is 2x. Plus, and then here, y squared x, we need to apply the product rule again. We got the first function, y squared, times the derivative of the second. The derivative of x with respect to x is 1. Plus the second function times the derivative of the first. We got something squared, so that's 2 times that something to the first power, times the derivative of what's inside. The derivative of y with respect to x is dy dx equals the derivative of a constant, which is 0. All right, now gather all of the dy dx's on the left side and everything else on the right. So on the left side, we're going to have x squared dy dx plus 2xy, and I'm reordering that to something I'm more comfortable with. 2xy dx equals, and then on the right side we'll have negative y squared minus 2xy. Now every term on the left has dy dx, so we can factor that out. And we're left with x squared plus 2xy, when we factor that out, equals negative y squared minus 2xy. And then we just divide by x squared plus 2xy. And the derivative of y with respect to x is negative y squared minus 2xy over x squared plus 2xy. And one final question. What happens when we throw a point in? All right? Find dy dx by implicit differentiation and evaluate the derivative at the indicated point. Some school of thought says solve all the way down to dy dx and then plug your point in. That's fine if you're going to plug more than one point in. All right? If you're going to plug more than one point in, you're going to want a formula like we have here. Dy dx equals negative y squared minus 2xy all over x squared plus 2xy. That's a formula you can plug multiple points in when you need multiple answers. I'm a different school of thought. If you're only doing it for one point, let's find our derivative, then plug the point in before solving for dy dx. Let me show you how that works. All right? So we'll take our derivative first. Here we got chain rule. We got 3 times x plus y squared times the derivative of what's inside. The derivative of x is 1 plus the derivative of y is dy dx when we're with respect to x equals the derivative of x cubed with respect to x is 3x squared. The derivative of y cubed with respect to x is 3y squared, and then there's a function implied inside of the y, and that's dy dx is the derivative of it. Okay? Now, traditionally we'd solve for dy and then plug our points in. I like to plug the point in first. It gets rid of all the variables. So I will plug in negative 1 and 1. We got 3, negative 1 plus 1 is 0. So that's going to actually fall off. 1 plus dy dx equals 3 times negative 1 squared is 3 plus 3 times y squared is 3 dy dx. Okay, because of this 0 right here, this is 3 times 0 times something, which, let's be honest, 0 times anything is a great canceller. 0 equals 3 plus 3 dy dx. See how it got rid of all those variables? Something more manageable. Subtract 3 from both sides. Divide by 3. The slope at the point negative 1, 1 is negative 1. All right? So, in review, doing implicit differentiation, you're going to differentiate before solving for y, because sometimes it's not easy to solve for y. Anytime there's a y there, you need to apply the chain rule and imply an x in there. So you're going to first differentiate with respect to x. Collect your dy dx on the left, and then factor it out, and then solve by dividing both sides. Unless you have a point, then you're going to plug the point in before solving for dy dx.